Okay, well, let's try this again here. Today we're going to talk about the periodic table. And I mentioned it briefly the other day when we talked about some scientists in history. Before I get to that, let's just start at the top. What is chemistry the study of? Like, what are you trying to study in chemistry? Matter, yeah. And so yesterday we talked all about some scientists over the years who helped contribute to our understanding of matter. Right? And really, what is matter? Well, the basic word for matter is stuff. Right? Like if you just want to use a generic word, matter is all the stuff we see. Right? But a chemistry definition is it takes up space and has mass. Okay? But really, like if it's a tangible stuff thing that you can touch and throw, and that's the stuff we have, right? And scientists for years have been trying to figure out, well, what is it made of? Right? And so here's a person, and a person is made up of compounds, but compounds are made up of elements. Well, for the longest time, scientists believed that the only things in the universe were the elements. But it was actually one guy who realized that there must be something smaller than an element. You know who that was that realized that elements weren't as small as it gets? What was his name? J.J. Thomson. Yeah. And it was because he was doing an experiment with something that he didn't know a lot about at the time. It was called the cathode ray. He didn't realize it, but he had actually been working with electrons. And he knew that it was smaller than an element. Why? How did he know it was smaller than an element? Say that loud. The cathode ray tube. Yeah, and he was able to weigh it. And he knew that its mass was 1/1000th the size of the smallest particle we knew up to the time, which is hydrogen. And so they realized that matter must not be, atoms must not be indivisible. That was actually where the word atom came from. It's the Greek word is atomos, which meant indivisible. They realized that matter must actually, like atoms, can actually be cut in half and cut into smaller pieces. And they started realizing that there were things like protons, neutrons, and electrons. And the cool thing about this is that the Thomson experiment actually helped to explain Dmitry Mendeleev's work. If you guys recall, Mendeleev, he wrote a whole bunch of properties of elements on some cards. I told you this story, right? He started grouping them together. Kind of like how my daughter would say, here's all the things that are red, and here's all the things that are shiny. I mean, honestly, that's what he did. He said, this reacts with water. So does this. So does this. Let's put them together. Well, over time, with the development and discovery of things like electrons and protons, eventually our modern periodic table was put together. So that's my goal today. My goal is to share with you guys how to interpret and how to use a periodic table. Does that make sense? So I'll read through my stuff here. Mendeleev did the periodic table in 1869, and he arranged all of the elements he knew of. I think this is actually really important. He arranged all the known elements by atomic mass, by how heavy they were, and placed them into columns and rows. I told you guys a story about how he left gaps, right? To me, that's one of the coolest things. Where he left a hole and said, well, we don't have this one now, but I bet you we're going to find it one day. And then the awesome thing is all of them have been found. Like, that is so cool to be able to make that sort of prediction. Okay, so here's a picture of, like, I saw this one online. It's a pretty cool periodic table. It's got a picture of what everything kind of looks like in terms of elements, in terms of, like, their, like, this is what this element looks like. Some of these things, though, they actually put down, like, the discoverer, like, the scientist they're named after. So, wait, first thing I need you guys to know. The periodic table has rows and columns, but really the important thing is something called the atomic number. And if you have a periodic table nearby, the atomic number, I don't have a slide of it. The atomic number would be if you have a square on the periodic table. There's a whole bunch of information it tells you. Like, for example, let's go with hydrogen. You'll see an H somewhere on the card. And then below the H, they'll tell you what you call it, hydrogen. Okay. Well, the atomic number is right up here in this top corner. This number right here is called an atomic number. And you guys will notice that as you look at your periodic table, basically it goes in order. But you have to kind of like go across and down. So up here, hydrogen, H is number 1. The next number is actually way over here. He is helium, it's number 2. Well, then to find the next number, you got to go back, kind of like when you read a book, right? Like you go across, and you go down to the next row. So the next one is Li, which is lithium, it's 3. And then Be, beryllium, is 4. And then kind of go across through like the hole in the table. to boron and carbon. Does that make sense so far? So all of these things are numbered in order, kind of going across and down, but there's actually some gaps in the table, and those actually I can explain a little bit later in today's lesson. Now, in terms of this table, it seems like then that there are 18 columns. And if you guys look at your particular table here, see how it numbers at the top, 1, 2, 3, 4, 5, all the way over to 18? So there's 18 columns here. Well, there's also some rows, right? Like across this way, there's a row and a row and a row. And the first thing that some kids think when they're looking at a periodic table for the first time is they think there are 9 rows. Because really, right? Hydrogen is in a row, lithium is 2, 3, 4, 5, 6, 7. And then there's those 2 rows right down at the bottom. The first thing I need to make sure you guys are clear of is that these guys right here, these bottom 2 rows there, are not actually rows on their own. What they've done is they've taken a whole section of the periodic table, and it actually is supposed to go where that little black thick line is right there. And to save space, they've kind of pulled some of the elements out and put them in a new spot, because otherwise the table should actually stretch out really long. So take a look where where that thick black line is right there. If you can see where LA is, it's number 57. And right next to number 57 is number 72. But that's not really the way you should read the table. It should go 57 for lanthanum, and then you should hop down to like this bottom row here, and then go to cerium, and then go across all the way over to this number, what do we got here, number 71, and then you've come back. Does that make sense? These 2 rows right here have actually been pulled out of the table and put down below just for space-saving reasons. Okay? So there are 18 columns, but there's actually only 7 rows. It looks like there's 9 rows. Is that clear to everybody here? But there's actually just the 7 right here. These 2 down here are actually supposed to be where that black line is. Otherwise, the table would stretch out like for forever. You need like a huge sheet. Well, another thing the periodic table gets divided up by then is, although it goes by number, is it's actually developed based on things that are either naturally occurring or things that are synthetic. Okay? So there's a lot of different categories we can have here. Now, I kind of have to give you guys like the short version of this because we haven't covered all the content yet, but if you want to know how to tell whether something is natural or synthetic, you have to look in the little squares here at a certain number. And in the square, that number for you guys is right up here. So for example, hydrogen, there's a number here of 1.01. Can you guys find that number on the hydrogen square, 1.01? Okay. It's called an atomic molar mass, and we're not ready yet to kind of talk about what it means because we got to build to that point. So if you can just like ignore it for now. I want to show you a different element though. Pick number 43. You guys find 43 on your table? It might take a second. 43 is called technetium. It looks like this. TC, number 43. It's spelled technetium, T-E-C-H-N-E-T-I-U-M. Okay, and I want to show you the difference here though. See how this one right here was 1.01 and it had decimals? Okay. Technetium, you might notice, is the number 98. And it has a bracket around it. Okay, if it has decimal numbers like this, it is a naturally occurring element, which means we can find it all over the Earth or in the solar system somewhere. Like, we can naturally find it. These ones right here that have brackets around it, they're synthetic, which means that they can only be found maybe in a lab setting or through like the process of like radio decay. You guys can come on in, by the way. Okay. Yeah, just give me one moment to finish this thought though. So that's how you tell the difference between natural and synthetic. Natural ones have numbers like 1.01 or 4.00. Synthetic ones have brackets, and then they have whole numbers like 98. That's how you tell whether it's natural or synthetic. Any questions on that? Okay. These guys have a quick presentation they need to give. I'm going to pause our video recording for a second. And Marley, you can have the floor. Okay, where did I leave off? We're talking about the elements. Okay, if I can give some advice, I already mentioned it earlier today. Today we're going to learn about a lot of different categories, like say synthetic versus natural. We're going to talk about metals, non-metals. So it might not be a bad idea while you got your periodic table out. If you're not someone who's really great at just knowing and memorizing words, write it down. I'm more than okay with that, right? Like, put little notes on the back of your table because you are a lot of cheat sheet. So just to make sure you're clear, if I ask you then, say, how do you tell between a natural or a synthetic? Look for that atomic molar mass, which I know we don't use yet, but if it's a decimal number, it's natural. And if it is a bracketed number, it's synthetic. Sound good? Okay, let's try a little game, just make sure you got it. So I'm going to pick an element on the table. I'll tell you where it is, just so you don't have to search for it. So I'll tell you what number to look for. And then you guys try to tell me whether it's natural or synthetic. Just make sure you get it. So let's go to number 48 for cadmium. 48 for cadmium. Would that be something natural or synthetic? Natural. Okay, cool.
I didn't even look at it.
Can you guys all find where 48 for cadmium is?
Found it.
Yes.
Okay.
What do you find?
48, the number there is 112.41 because it's got a decimal number and it's not in brackets, it's natural. What if I were to give you number 84, which is polonium? 84, which is polonium. Synthetic. Can you guys find the 84, the number there is 209, but it's in brackets? That's how you tell the difference. You find 84? It takes a little while to get used to trying to figure out where the numbers are. They are in order, you know what I mean? Okay. Let's try a tricky one here. You ready? You need to find number 61. 61. Yeah, and 61 I was tricky because it's actually like in like those bottom rows. That's where you find 61. And then its number was 145, so it's synthetic. Does everybody feel like they're okay on that idea? Okay, cool. Let's move on then to some other categories and properties we have on the periodic table. So, natural and synthetic is one kind. Another one is known as the metals. Pay full attention, okay? Metals and non-metals and metalloids. We have three categories on this next section here. So, metals, you guys kind of know what metal is, I'm sure, right? Like, metal is this, right? No, we're good. Okay. Alright, so like here's a lot of examples of some metals you might know. Almost all of the metals on the table, like 3/4 of them are actually metal. And you guys might recognize a few of these terms because we've used them already. Things like malleability. What's malleability again? A sheet, yeah. Or ductility, which was wires. Okay. And so if you want to look for metals on your periodic table, you have to look on the left-hand side of what's known as the staircase line. So I need to show you where the staircase line is. It's a little line we draw on the table right here. It goes right there. You guys see that one on your table? It's the other line on the table that's black. There's two on the table. One was like that two little spot I showed you. Guys, I'm not getting full attention. Can I get it, please? Yeah. There's that two little spot right about here, somewhere in there where there was a bold line. Okay. And then the other one is this bold line right here. This is known as the staircase line. And we use it to try to figure out where the metals are, which are usually over here. And on the other side of the metals line are the opposite of metals, which we call non-metals. Okay. So that's what I have my next two slides about, is metals are found on the left-hand side of the periodic table, and non-metals are found on the right-hand side of the periodic table. Now, I have to point out a similarity, but it's not a rule that's always there. Can you guys see how like these different boxes we have here, how they're colored in different colors? Okay. All the yellow ones on here, over here, are metallic solids. Okay, and that's another good way for you to be able to tell. But there's a few exceptions. Mercury, which is right about here, Hg, mercury, is actually a liquid. But even though it's a liquid, it's still considered to be a metal. Okay, so the point I need to make to kids is that solid doesn't necessarily mean metal always. There is one exception. Liquid mercury is actually considered to be a metal. Okay, it has similar properties. The non-metals then are the things over here that are green or blue, or there's actually one other liquid, bromine, on the table. And so many of them are liquids and gases, but there are some that are still solid, like say carbon. Carbon is green, which is a non-metallic, non-metal solid. But in general, here's a good rule of thumb. If it's a solid, it's probably a metal. And if it's a liquid and a gas, it's probably a non-metal. But that's not like a for sure kind of rule. There's a few exceptions. Okay. There's actually a third category, because there's some things on the periodic table that they really act like metals because they're strong and they're ductile, but they might not be malleable. Or they might conduct electricity like a metal does, but it might be brittle like a non-metal. And so we give a third category of like the wishy-washy ones that are kind of in both categories. We call them metalloids. Here's the advice I'd give you. On your periodic table, I'll try to find them where they are. Point them out here. Just put a little note, like a little star or something next to it so that you know that they're metalloids. So if you can see my table right here, B up here, number 5, boron, is a metalloid. It kind of does both metals and non-metals sometimes. Then go down the next step on the staircase to silicon, Si for silicon. Drop another step below on the underside of the staircase is germanium. So go straight down from silicon. Then go over to arsenic, that's also one. You can either say it antimony or antimony, depends on your inflection, but straight down from arsenic is antimony, Sb. Then over from it is tellurium. Below tellurium is polonium, and next to it is astatine. Just put a little star or something on your table just so you know those are the metalloids. But in general, things can be categorized as either a solid metal, which does things like, I'm just going to find the properties again. Metals are conductors. They're malleable. I can make a sheet of copper. Ductile. They're usually pretty strong and durable. Whereas your non-metals aren't good at that. Let me give you an example. Can you guys find number 8, which is right here, oxygen? You've probably all heard of oxygen. We breathe it. Could I make a sheet of metal out of oxygen? Any sense whatsoever, right? How do I make oxygen into metal? It's a gas, right? And I mean, some of these things you'll know you've seen before, like say, pardon me, carbon. Carbon is number 6. It's kind of in that wishy-washy zone a little bit though, where although it is a solid, it's carbon, like we use carbon in our pencils, right? You know that? Your pencil lead is made of graphite, which is carbon. It's not actually lead. It's a poor choice of words. But it actually is considered a non-metal. And the reason why is that carbon doesn't do certain things that other metals do. Like I can't make a sheet of carbon very easily. You know how we use pencil lead? It actually breaks apart quite easily, which is important because that's how it stays behind on the sheet of paper, right? Whereas like copper and aluminum, they don't behave in similar ways. Okay, let's move on then. So those are some properties you guys should know. Other vocabulary I want to be aware of. It's called a group. Okay? As you go up and down the periodic table, if you have a column, they're known as groups. And so there's actually 18 groups on the periodic table listed from 1 to 18. And in general, as you go up and down in columns, they actually have very similar properties. Let me give you an example here. Group 1, which would be the very, very first column, it has H for hydrogen, Li for lithium, Na for sodium, and all the way down. They all have very similar properties in that they're all very reactive with water. And so when Mendeleev was trying to put his periodic table together, this is one of the things he did, is he categorized them based on similar properties. So up and down, we call them groups. And there's actually 4 groups that I want you guys to know their special names of, because we actually give them like a quick name. Well, they're not quick, but based on certain properties here. Group 1 is known as alkali metals. So what I might recommend is above the first column right here, maybe you might want to write this one down, alkali metals. And they're very unique in that they all react very violently with water. Next week when we do one of our labs, this is one of the reasons why we need a fume hood, I'm going to put some sodium in water. And this is actually where I had my problem last year. It will violently explode, and I actually had it blow up a beaker last year. Which sounds cool in theory. Talked to the 5 kids in the class that were terrified at the time, because it was like a gunshot going off. It was yeah, it was a small group. But yeah, I mean, so I do want it to light on fire next week, but I'm hoping that it won't actually explode the beaker, because that was actually a little scary. Yeah. The beaker itself, like literally, like, and if we weren't in the fume hood, like I have no doubt we would have had glass shards in us. You know what I mean? Like it would have been like shrapnel. So that is why I got to take safety very high, because I don't want you guys getting hurt. But I do want to be able to do some cool stuff. So anyways, next week when we do another lab, I'll show you guys what sodium looks like in water. All of these alkali metals are very reactive with water. We actually can't store them in a typical like jar or beaker or something like that. They actually have to get stored under oil. And the reason why is that there's water vapor in the air, and that water vapor in the air would actually react with it. And so it actually has to be stored completely submersed in oil, otherwise it might actually spontaneously combust. Which sounds cool again, but like I said, very dangerous. Okay, group 2, right next to it, it's Be for beryllium, Mg for magnesium, Ca for calcium. They also have very similar properties to each other. So their name, as you can see here, is alkaline earth. It's like alkali, only keep going, alkaline earth, and that's group 2. They don't have anything nearly as cool as exploding in water, but they're all very similar to each other. They all make a lot of very similar types of salts. Not salt you put on like your corn on the cob or potatoes, but chemical salts. Okay, the other ones that have common names I need you guys to know is group 17, which is way on the other side of the table over here by what we call the non-metals. Group 17, if you can see it, starts with number 9, fluorine, number 17, chlorine, 35, bromine, in that group there. We call those ones halogens. And they're very unique in that they're very, very reactive. They have a high tendency to form compounds. Which is very curious because the group right next to them actually has the opposite properties. These guys in group 17 love to form compounds. The ones in group 18 never form compounds, or at least very rarely. And so we have a special name for them. We call them either noble gases or inert gases. And I have a cool story about how this works. The noble gases, the reason why we call them noble is because it kind of harkens back to like the day of like when like the royals, there were like, you know, the royal families and like there's like the serfs. You guys ever talk about that in social studies? You know, your peasants and your royals, right? And the nobles, they kept their noses in the air. They didn't want to be associated with anybody else, right? Like it was not cool for you to be a noble associated with a peasant. You know what I'm saying there? Mm-hmm. Well, the noble gases, we call them that because they don't want to combine with anybody. They are like the uptight, like noses in the air, we do not hang out with your kind, you know, kind of people. If you're elements. Does that make sense? So that's actually why they're called noble gases, because they're non-reactive. The chemical word for that, though, is actually called inert. If you ever come across the word inert, it means doesn't react, doesn't combine, like wants to be by itself. So it's actually kind of cool that they're right next to each other. One group right here loves forming compounds. The other one hates it, and they're right next to each other. What's that? Yeah. Okay, so those are groups. They go up and down. You should know at least 4 of them that have a common name. Now, going the other way on the periodic table are known as the periods, and those are rows. So there's actually only 7. Okay, I know I mentioned this before. It looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9. But hopefully I'm clear on this. There are not 9 rows. This is a space-saving technique. Right here is where all of these 2 rows should be inserted. Now, I don't have it written in my notes, but periods are based on orbitals. We talked about this yesterday a little bit, where Rutherford and some other scientists, they thought that maybe there was a nucleus and that electrons orbited around. And granted, we now know that they don't go around in circles. There were actually some problems with the circle theory, but just pretend the circle theory was true for a second. Bohr realized that electrons literally jumped from this circle directly to that circle right there. They literally teleported, which I think is the coolest thing in the world. Right? Anyways, there are 7 known orbital levels. Okay? And each known orbital level is each period going down. Does that make sense? So each time that we go down, it's a new orbital. Another word we might use for it is we might call it an energy level. Because the reason why orbital doesn't work is that they don't actually orbit. When the word was starting to be used, they thought, hey, maybe these things go around in circles like planets do. Now that we know that they actually like exist in like bubbly cloud kind of stuff, the word orbital really isn't a good choice. So use this instead, energy levels. This is your first energy level where electrons could be. This is the second one, the third one, the fourth one, etc. Does that make sense? Cool. All right, let's move on. So let's talk a bit more about these atoms. I've been using this terminology with you guys so far, but I want to make sure you all know the words, and we have them written down. There's actually 3 different types of things we call subatomic particles. Okay. Up till Dalton, scientists thought that the atom was as small as it gets, but we now realize that there's actually smaller stuff. There's at least 3 smaller pieces, and there's probably more than that even. The three pieces are protons, neutrons, and electrons. I've used those words with you guys before, right? Just so that I use the proper, like I have a little shorthand so I don't have to write it out. If I ever draw this symbol right here, E, with a little negative next to it, that's my short way of writing an electron. E for electron. And the negative because, words I can say. Electrons are negative. So E negative is because electrons are negative. The opposite of an electron is a proton. Protons are positive. So I write P positive for protons. And then neutrons are neutrons neutral. Neutrons are neutral. They don't actually have a charge to them. I give that an N. I put a little 0 next to it. Just because you know how there's positive numbers and there's negative numbers, which number is not positive or negative? So, anyways, just if you ever see me do that, because I realized that a second ago. I was drawing on this slide right here, and I used a little E negative, and I realized maybe you didn't know what I meant. But if I ever use an E negative, that's a short way of writing an electron. Fair enough? So, anyways, we now know that our stuff is made up of protons, neutrons, and electrons. And we understand, due to Rutherford's gold foil experiment, that the nucleus has the protons and the neutrons. And the electrons actually have to kind of hover around. They don't actually orbit, but orbit works for like a good picture for nowadays. So what I want to do today is talk with you guys about some theories about how the periodic table works according to protons, neutrons, and electrons. Here's the first word I need you guys to know. Atom. Okay. All atoms are neutral. And when we talk about things on the periodic table, we're usually talking about atoms. Okay? Atoms are neutral, which means that if they're going to have no charge to them, the number of protons and the number of electrons has to be the same. Okay? Imagine I have 5 positives and 5 negatives. Can I see how they like balance each other? That's neutral. But if I have like 5 positives and 4 negatives, then there's like 1 left over. I have another word for that, and I'm just going to write it down now. It's called an ion. Okay. Ions are not neutral. I've got slides on that later, but there's another 2 categories. Atoms have no charge. Protons and electrons will be the same as each other. Ions, you'll have more of one than the other. Well, one of the other cool things about the periodic table is that, you know that atomic number that we talked about where it literally lines them up 1, 2, 3, 4, 5? That atomic number, do I have a slide on this here? I don't have a slide on it yet. I'm going to come to it next here. The atomic number actually tells you how many protons you have. So if you're wondering how many protons any given element has, it's the number in the form. So like hydrogen has 1 proton, and helium has 2 protons. And so if I ask you, like, say, how many protons cadmium has, you just have to know where cadmium is on your table. It's number 48. Well, then it means that's 48 protons. That's actually how we name these things. It's based on how many protons they have. I have such a silly analogy for it. I use analogies all the time. But you guys ever watch the Smurfs?
Yeah.
You know how, like, the Smurfs, literally their names are based on their personalities? So, like, Grumpy Smurf is called Grumpy because he's grumpy, right? Well, similar-ish concept in chemistry. The number that we have is based on its protons. Okay? We call hydrogen hydrogen because it has 1 proton. Everything that has 1 proton is a hydrogen. Everything that has 2 protons is a helium. Everything that has 3 protons is a lithium. So these things are given their names based on their protons. Kind of like how the Smurfs are given their names based on their personalities. So anything that has 5 protons, number 5, we call a boron. Okay. Now, we can change neutrons and we can change electrons, but protons are what defines our names. Does that make sense? So, the electrons we can change, because remember how the electrons kind of were going around in orbitals? We can actually change those, and they actually go in energy levels. And I like to use an analogy of like a hotel. The first energy bubble that can hold electrons has 2 rooms in it. And that explains why the first row of the periodic table only has 2 to it. Because literally there's only room for 2 electrons there. The next energy level can actually have 8 rooms in it. So you can actually have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And so you actually know how full each energy level is based on how many elements there are going across. So the first row has 2, then there's 8, then there's 8, then the next row actually has 18. And so like each energy level can actually have different numbers of electrons. Here's a slide that just kind of talks about the 3 different charges. Protons are positive, we find them in the nucleus. Neutrons are neutral in the nucleus. And electrons are found in orbitals, but sometimes we don't want to use that word. Sometimes it's better to say that they're found in energy levels, just because they don't actually orbit. So here's my goal of the day now. Now that we kind of talked about the periodic table, I'm going to give you guys a task. And the task, I'm going to go right to the very, very last slide. So if you guys have your notes nearby here, this is my goal to get to, and hopefully I can do this in 20 minutes. I need for you guys to be able to tell me who is going to be someone who has 17 protons, 20 neutrons, and 18 electrons. And so I need to try to tell you how to identify who this would be on the periodic table. It's kind of like a matching game. Okay? And so I have to talk about each of these 3 things one at a time. What does protons help us know about? What do neutrons help us know about? And what do electrons help us know about? So I'm going to focus on each of these 3 subatomic particles for the next few slides. And then we're going to do this thing last. So let's go to here. The 3 different types of subatomic particles helps us with 3 things. I've already talked about this one. Protons tell us the identity of who it is. So just like we call him Grouchy Smurf because he's grouchy. If there are 7 protons, we call it a nitrogen. Because number 7 is nitrogen. Does that make sense? So protons is actually a really easy one. Okay? If you want to know its name and its protons, they're linked to each other. The number of protons, which is the number on the corner of the chart there, that's how it gets its name. So that's known as an atomic number. Now neutrons, they mess things up a little bit though. Neutrons have no charge, and they affect what's called an isotope, which basically affects its mass. Okay? They make elements heavier. If you have more neutrons, it's like adding more fat. It makes it heavier. Okay? And we use what's called a mass number to figure that out. I'm going to show you that on another slide. The last thing is electrons. Electrons will help you figure out whether things are charged or not, and that's the difference between an atom or an ion. And I already mentioned these words a bit. Atoms are neutral. Ions have a charge. So those are the 3 things we're going to focus on. Protons, neutrons, and electrons. So let's do a slide. If I want to talk about the atomic number is always a number of protons. And there's a few ways we can find that. If you got your periodic table, it's just what number is there. But you might see a notation that looks like this. C with a 6 and a 12 up top here. You might see a notation like this. Well, this bottom number down here is how many protons you have. So if you ever see a notation like this bottom number right here tells you how many protons you have. And if you guys look back at your periodic table, see how number 6 is carbon? We call it carbon because it has 6 protons. And that's actually how we order the periodic table. Well, to figure out how many neutrons you have, that's how you need to use this top number. And I've got a slide right here to help you figure this out. Hydrogen right here, see how the bottom number right here is always 1? Why is this bottom number right here always 1? Because hydrogen always has 1 proton. Why? Well, because that's why we call it hydrogen. Hydrogen is defined by its number of protons. But see how this number up here at the top is changing? Here it's a 1, here it's a 2, and here it's a 3. That number tells you how heavy it is. Now, protons and neutrons are quite heavy. Electrons are actually super, super light. We already talked about this. Electrons were 1/1000th the times the size of some of the atoms we know about. So electrons really don't count to mass. So this top number is called the mass number, and it basically is how many protons you have plus how many neutrons you have. So you can kind of see in this example right here, we know that hydrogen has 1 proton because it's number 1. If there's a 1 up top right here, then there's only 1 thing there, and it must be the proton, so there are 0 neutrons. But if I put a 2 right here, guys, you're going to want to pay attention to this, okay? Okay? I know that I'm talking for a long time, but I mean this with love. You're in high school. I need you to be able to focus for an hour, okay? Okay. This top number right here tells you how heavy it is. So it has a weight of 2. How many protons does hydrogen have? It has 1, right? Because it's number 1. Well, if it has a weight of 2 and one of them is a proton, well then by default the other one must be a neutron. So you can see right here it says there's 1 proton and 1 neutron adding up to 2. If I put a 3 right here, well, hydrogen, because it's number 1, has 1 proton. But how does it get a weight of 3? Well, there must be 2 neutrons. See how that works? I'll try one more example here. Here's carbon. See how all 3 of these carbons have a 6 on the bottom? It's because they have 6 protons. Carbon is defined by its protons. Grouchy Smurf is defined by its personality. I know it's a dumb analogy, but I hope that makes sense. This is why we call it what we call it. Its protons never changes. This carbon right here is pretty lean. It has 6 protons and 6 neutrons. It had to have 6 protons, but if it has 6 neutrons, it weighs 12. Well, here's a carbon that weighs 13. Well, it just means that it has more neutrons in it. So it has to have 6 protons, but now it has 7. Or now it has 8. So a really easy way to figure this out is if you want to know how many neutrons you have, just subtract these 2 numbers, and you'll know how many neutrons there are. That makes sense. So let's try a little example. I'm going to write out an element here. Let's go with Al 1324. So, where are you going to find Al on your table? Well, the 13 at the bottom gives it away. The 13 means you're looking for number 13. So scan through until you find number 13. What do we call it? Well, because it has 13 protons, we call it aluminum. That's why it has its name. My question for you is, how many neutrons does this aluminum have? Well, if there's 13 protons, and you have to eventually have 24 total, how many neutrons do you need? Not 9, yeah, good call. 11. I can't do math apparently. Right? Because 13 plus 11 would be 24. That makes sense. But it's possible for there to be a 26 Al13. All that means is that aluminum would then still have 13 protons, but if it had 13 neutrons, then it adds to 26. You guys follow that? Now that's one way of writing it, but sometimes it's a little redundant to put this 13 right here, because the aluminum gives away there's got to be 13, right? Because aluminum is number 13, we know that bit to be true. So sometimes we write it in words. Suppose we might just call it hydrogen 3. And if we ever put like a number afterwards, that's how much mass it has. So I want to flip ahead to my last slide if I could. Can you guys jump ahead to the last slide? I want to talk a bit about protons and neutrons now. So let's try this one right here. Ignore the electrons. We're not yet to that spot, but let's just do the protons and neutrons. I'm going to ask you guys to try to tell me who would have 17 protons and 20 neutrons. So let's start with the protons. Who's number 17? It's way over here. It's chlorine. So we now know who this is. This guy is a chlorine. It's chlorine. But what type of chlorine? How heavy is it? Well, if it has 17 protons and 20 neutrons, we would call you a chlorine 37, because these two things added up to 37. Does that make sense? Okay, let me try one more. 10 protons, 11 neutrons. The 10 protons gives away who it is. So find number 10 on the table, neon. Okay, so now I know that it's neon. The question is, how heavy is this neon? In chemistry, we're very impolite. You know how you never should ask a person how heavy they are? In chemistry, we're always doing that. We're like, which one are you? Are you the heavier one or the lighter one? So, and this will be number 21, right? Because 10 and 11 is 21. Does that make sense? I'll leave the last ones for later, because I want to talk about electrons for a bit now. But hopefully that helps you a bit with the protons part. So the next thing I want to talk a bit about are electrons. Now, remember how we talked about how the previous models of matter, electrons were like literally inside the raisin bun, inside the muffin? But they realized that that's not actually where the electrons are. The electrons are like on the outside in what we call the orbitals or energy levels. And that's what I've got right here. Electrons are found in energy levels. And we can try to figure out a little bit about how those electrons are going to move based on their location on the table. Because electrons have the ability to form what are called ions. If electrons gain or lose electrons, they form ions. But if there's equal protons and electrons, it's still an atom. Remember how a while ago I mentioned that atoms are neutral? If you have 5 protons and 5 electrons, you're an atom. But if you have a different number between the two, we call it an ion. So I want to hop back to that slide I had there. And I want to talk about these two that I have. Take a look at this proton right here and this electron right here. Is it the same number of each? And we have equal protons to electrons. Who wins this fight? The electrons or the protons? The electrons win. So because of that, I'm going to now tell you that this is a chlorine ion. Now, the last question I have for you is, by how much did they win? By 1. Okay, so what we would then say is that there is a -1 charge because there is 1 extra electron. And so it is a charged ion with 1 extra electron because the electrons have more than the protons. Let me try another example to help solidify this. We already hopefully agreed this was neon 21. So here's my question. Is it an atom, which is neutral, or an ion, which is charged? And hopefully you can see it's an atom because, look, there are 10 protons and 10 electrons. So because of this, nobody wins the charge fight, and so this is an atom, which actually makes sense compared to something I told you about earlier. Can you guys find where neon is on your table? It's right there, number 10. It falls into a group that we call the noble gases. For the noble gases, they don't like to react with anyone. Well, ions like to react with things, atoms don't. And so this actually kind of makes sense from that point of view. Because of the fact that it's an atom, it won't combine with something else. But chlorine loves to combine with things. Like, for example, anyone ever heard of NaCl? Yeah, very common thing. The reason why is that chlorine has a negative charge. It likes to be attracted to other positive things. Well, I want to try a couple more examples on this slide here, and then I'm going to go back and finish off my notes. So let's talk through this one here. We got to find someone with 7 protons. Okay, so number 7 on the table is nitrogen. Now it's got 8 neutrons. So basically now I'm asking you how heavy is it? Well, its total weight, 7 plus 8 is 15. Then my last question is this an atom or an ion? Well, then we look at the protons and the electrons compared to each other, and we try to figure out whether or not it has more of one than the other. Well, they're the same, right? So this is an atom, which means it's neutral, which means it wouldn't want to combine with something else. Well, let's try the next one below. Still got 7 protons. Well, it's still nitrogen. We define our chemicals by their protons, just like we define our Smurfs by their personalities. I know it's dumb, but I need to make sure that's really solidified. The protons tells us who it is. Well, now this one has 9 neutrons. What's the only thing that changes? Yeah, 9 plus 7 is 16. So all this means is this is a nitrogen that's slightly heavier. I want to talk about that for a second. John Dalton had a theory. He thought that all nitrogens were the same as each other. He thought that this nitrogen molecule here was exactly the same as this one over here, which was exactly the same as this one over here. He didn't know about this at the time, but he was actually wrong. Not all nitrogens are the exact same as each other. There are some that are just heavier than each other. We call them nitrogen based on their protons, but there are some that are actually lighter and heavier. Wait, last one here. Clearly there's still 7 protons, so we're still stuck on nitrogen. It's still a 16, right? Because of the fact that 7 and 9 adds to 16. But here's the change now. What if there's an extra electron? What if somehow nitrogen found an electron just lying there on the street and somehow gained an extra one? Because it can do that, by the way. Protons are so tightly packed in the nucleus, you cannot change the protons. It's not possible. You can totally change your electrons. Right? So let's say it has an extra electron. Who wins the fight? Well, there's more negative electrons than there were positive protons. So we're now going to call this an ion. And this one actually also has a -1 charge.
That isn't listed in the nitrogen ion charges.
No, nitrogen often has a -3 charge. Is that what you're looking at there? Yeah, I just made some ones up here. I get what you're saying here. I just made one up. So what I need for you guys to be able to do is go like both directions here. If I were to tell you these species right here, could you tell me what we're talking about? Or what if I went backwards? What if I were to ask you to tell me about let's do one more made up example here before we're done for the day. What if I were to ask you about a calcium 41 ion with a 2+ charge? Could we figure out what a calcium 41 ion with a 2+ charge is made of? You know what I'm saying here? We're going the other way this time. You want to take a stab at it?
20 protons, 21 neutrons, 18 electrons.
Okay, so you blitzed through that. Let's talk through the pieces. You're right. So let's talk through the first little bit here. How do you figure out the protons? Calcium is defined by its protons, right? So you got to find where calcium is on the table. And at first, this takes a little while because you have to be able to find calcium. Calcium's right here, Ca, it's number 20. So because it's number 20, we know that it has 20 protons. Does that make sense? That's what the calcium tells us. All calciums have 20 protons. The 41 tells us how heavy it is, protons plus neutrons. Electrons don't count, they're super duper light. Well, if it adds up to 41 and 20 are protons, then 21 better be neutrons. Okay? Last bit. There's a 2+ charge. Now, this is what a lot of my students, especially in grade 11 and 12, when I first start teaching them, they forget about this. They think if there's a 2+ charge, it just means we need to add 2 more protons. You can't add 2 more protons, because if you add more protons, it's no longer called calcium. Does that make sense? Let me say that one more time. You cannot add protons, because if you add more protons, it's now a different thing. Yeah. Okay. So you can't add protons, but you can totally mess around with electrons, because electrons aren't fixed in the nucleus. So how do you have 2+? Well, let's say you had 18 electrons. Now there's more protons than electrons. So what I need you guys to be aware of is that there's 2 possibilities. You can either get extra electrons, or you can lose electrons. And I just want to show you some quick slides on that, and then we'll call it a day. So let me go back to some slides I skipped. I do this a lot, by the way. Here's 2 slides on formation of ions. Here's the 2 ways these things can occur. Let's say that sodium, as an atom, was supposed to have 11 electrons and 11 protons, because it's neutral, it's an atom. Now let's say that sodium somehow manages to lose an electron, which is totally possible. Electrons can be lost all the time. Protons can't, though. If you lose a proton, it changes who you are. Okay, stay with me. I know I'm almost done. Okay. Well, right here, if sodium loses an electron, it's now a charged ion, because now there's more protons than electrons. And you might see it written like this, Na, with a little plus up in the corner. That tells you it's charged. If you ever see Na written by itself, it means that it's not charged yet. So that's one possibility. Someone could lose an electron and become positive. We have a name for that. You may want to write this one down too. We call that a cation. Someone really smart, one of my students came up with this brilliant analogy. In order to remember this, he realized that cats have paws. And so he realized that cat ions are positive. But it works actually, right? So if you're not sure which one is which, if something is positive, we call it a cation. Well, the opposite of something that's positive is negative. And so here's the opposite one, chlorine. Chlorine as an atom would have 17 electrons and 17 protons. But what happens if chlorine found an extra electron just lying there on the street and picked up an extra electron? Well, now it would have 17 protons, but it would now have 18 electrons. It's gained an electron. We give that the name an anion because now it's negatively charged. And here's the cool thing about that. Let's say that you have a sodium, which is a positive ion, and you have a chlorine, which is a negative ion. This is how compounds are formed, because positive and negative stuff likes to attract each other, and that's how salt gets formed. And that's what we're going to focus on later. So here's what I'm hoping we learn for the day. I'm going to stop my lesson here because we're getting close to the bell. Kind of 2 parts to my lesson. The first part is the periodic table. If I were to give you some definitions, you guys can pack up. I'm okay with that, but make sure you listen, okay? Can you multitask? Okay. Do you know what a group is? Do you know what a period is? Do you know where to find the metals, the non-metals, the metalloids, the synthetics, the naturals? Okay? We learned a lot of terminology today. I would highly recommend, if you don't memorize them, write it out on your sheet. Okay? The other thing we talked about is the internal structure of matter. Protons, neutrons, and electrons. I need you guys to know that protons are what identify our substances. That's what gives it its name. You can add more neutrons, it makes it heavier. You can also move the electrons around, and that maybe will make it an ion of some kind. Okay. I need for you guys, and if you haven't gotten to looking at your assignment, the last question on your assignment looks something like this, where I'm going to say, let's just do one last example here. I know you guys are packed up, but if I were to tell you that I'm asking you to do a barium, let's say 100 atom. Do you guys feel like you now have the skills to tell me how many of each of the three things are there? How would you figure out, like, that's not do it, but how would you figure out protons?
You find the area.
And that's its number, there's its protons. How would you find its neutrons? Subtract it from 100, yeah? And then if it's an atom, well, however many protons we figured out, that must be how many electrons there. Does that make sense? Good. Okay, guys, one last thought, and I'm going to let you take off, because I know the bell's about to, well, we're not going to have bells. Okay. So wait, tomorrow is the due date for your assignment. Okay, so now, what I'd like to recommend is tomorrow when I give you guys some work time, and hopefully today during flex and for homework and stuff, that you work on that assignment. I highly recommend do your assignment before you do your quiz. I find some kids, they like try to do all the homework later, and they write the quiz first. But if you do the assignment before you do the quiz, here's the answer key. I will let you mark it yourself. And I feel like this is the best way to help you learn, because if there's mistakes that you're making and things you're not doing well, if you can catch them before you write the test, that solves the problem. You know what I'm saying? But if you try to write the test first and then do your assignment, you usually don't do as well. So the answer key's on the board. Here's the rules, guys. Okay? If you mark it yourself before the weekend, it's on time. You can mark it. I'll just do a quick look over to make sure it's good, and you can throw it out and not count it if you take it. So like if this assignment goes horribly wrong, you just don't have to count it. Does that make sense? But if you don't finish it, what's that? It's due tomorrow. But if you don't finish it by the weekend, it's not a big deal. I'll mark it for you. Like, I mean, I'm going to make you do it at some point here. But the one catch, though, is that it has to count. You know what I'm saying here? So if you want to have the option of being like, well, I guess I might fail this one. I'm only going to get a 47. You know, sometimes what my kids do is they just mark it anyways. Because to me, this is the most important thing. I need to give you feedback. If you don't know how you're doing on the first assessment, how are you going to do on the second one? So it may actually be better for you to mark it as it is by the end of tomorrow, even if it's only partly done. Take a 37%, learn from the mistakes, because hopefully you'll get better, and then you can throw it out. You get 5 things you can throw out, so you can use that as one. And you can't throw everything out, but you can use that as one. Everybody clear on that? Alright, cool. Tomorrow's a work day. You guys can take off, but I would strongly recommend work on your assignment during flex if you can. Whatever you want. Let me move out of your guys' way.
I didn't do,